So here we'll be talking about spatial descriptions and transformations, right? So, we'll basically be looking at how we can solve these spatial descriptions and transformations problem using MATLAB Robotics Toolkit. So here I have the theory parts that we discussed in class listed. So I will do this as a small recap so that no one misses anything, right? So that would be this would be somewhat like a recap of the basic theories that you already know. So when you talk about spatial descriptions, right? What are spatial descriptions? So when you want to locate something 3D vector space, right? So how would you do it as a human? So as an example, we'll consider a scenario where you want to cross the road, right? So say you are going to cross a road and there's a vehicle approaching, right? So you get this intuitive understanding of whether the vehicle is far or close by, right? So you get a feeling whether so you're crossing the road. So say a vehicle is approaching, you know as a sense, right? Whether the vehicle is far or close by, and whether it's possible for you to cross the road before the vehicle reaches you, right? This sort of automatically happens. You don't have to calculate the speed of the vehicle. You don't have to calculate the location of the vehicle, the location you are in, and then do a mathematical, calculation to estimate whether you can cross the road or not, right? You don't have to do that. You have the sense, right? You call that intuition, right? But when it comes to robots, they don't have this particular intuition or the sense, right? You have to manually view it. Not only robots, anything, right? If you want to have any artificial object, you have to either teach a model to understand these concepts like depth and force and all these things, right? If not, you have to manually sort of program the device to understand how the aspect of depth and all these things. So the easiest way to do this is to understand the relationship between two objects in 3D vector space. So now when you talk about the relationship between two objects in 3D vector space, there can be two types of motions that can happen with respect to another object. So one is, as you all know, translations. The other is rotations, right? So translations are basically, if I annotate here, spotlight. So if there's point A here, and if there's point, say, B here, this is a translation, right? I'm moving from A to B. It's a translation, right? So initially at time 0, I'm here, and say at time t, I'm here, right? This is translation. Rotation is simply, if you have this coordinate frame here, I can rotate this coordinate frame by an angle of, say, theta around Z axis, right? So now if I rotate this, the Z axis will be here and the Y axis will be here. X will be at the same point because I rotate around X, right? I rotate around X. So the angle will be theta, right? If this is theta, this will be theta, and this will be also be theta. So this is basically what rotations are. Now, how do we describe them, right? So descriptions basically means, so these are the transformations, right? These are the two types of transformations that are available. These rotations and translations. So descriptions basically mean how we describe these, transformations in a mathematical manner. So this is basically what the topic actually stands for: spatial descriptions and transformations. So how we describe these transformations. So how do we describe a translation, right? So this is the first transformation. The most simplest type of transformation is a translation. So you all know from your basic fundamental knowledge that how you describe a translation is using a position vector, right? And by the way, I'm using one of my handwritten notes, right? So it might sometimes not be clear. I tried my best to make it clear because I didn't have time to prepare some slides or anything. So I hope this is clear, but I try to explain all the elements that I've written so that you can understand what's going on, right? So say this is a manipulator, right? It's a manipulator. So there are two joins. So we assume there's a base here. So base, say it's fixed here. Two joins, two revolute joints. You can rotate around this axis. And there's the end effector here. So if we draw a Cartesian frame here, so if I can explain this here. So in this case, so if you want to estimate the position of any of these objects here, there's a cylinder here, there's a box here, with respect to this base. Now you have this coordinate frame. With respect to this frame, you can identify the translation of this. So it will be, so if you want to identify the translation, we're talking about translations here, right? If you want to understand the translation of this particular box with respect to this base, you just draw a position vector from the origin of this frame to this frame, right? Say you want to identify the translation between this cylinder and the end effector here, then you draw or you get a position vector from here to here, and then you can get the position vector from here to here, from here to here, to this joint, and from this joint to this joint, and from here to here, and from here to here, and then you can compute an algorithm to get the relationship between this and this, and also between this and this, right? So this is actually how these things work. So we'll look at that in detail. So we move on. So now how we describe the translation is using a position vector. So here this what the notation stands for is the position vector with respect to A of this particular point, right? Is given by these three elements: position with respect to X, Y, and Z. So that is, I think that is clear. So you get a 3x1 position vector with these three elements, right? So and if you want to describe the rotation, there's something called the rotation matrix, which we already have discussed, right? So say you have this frame here, and we'll forget this position vector for the time being, and we'll imagine. So just imagine that this particular frame, I pick it from here and I keep it here, like this. Like this. So I with the same colors, I come and keep it here, right? So just for the time being, we just forget about this position vector. So it means that this is a pure rotation, right? So rotations can happen. So these rotations now, in this case, this will be rotated around all three axes. We can imagine, right? So you can see since none of the axes are overlapping, we can assume that this rotation has taken place around all the axes, right? So so in that case, we can sort of notify this as the rotation of B with respect to of B around X with respect to A, the rotation of B around Y with respect to A, and the rotation of Z-axis with respect to of B with respect to A around the Z-axis. So these are the three rotations, and we can demonstrate these rotations using a rotation matrix. So rotation matrix, the derivations you can go through what has been covered in the lecture. So I'm not going to waste my time in deriving these, right? Since this is a lab class. So so these rotation matrices, once you derive, you will get something like this, right? So I'll get back to that in a moment. So here once again, so if you want to say represent something, if you want to represent some coordinate frame with respect to something, you can basically use this idea or the concept of the frame, right? The frame simply has two descriptions, which are the rotation matrix and the position vector. So if you are talking about the coordinate frame B with respect to A, the position vector between the A coordinate frame's origin and B coordinate frame's origin, that will be the position vector, and also the rotation matrix. This will be simply what will be included in this frame's details, right? So we'll look into this as we do an example. You will understand it further then. So you can use this to map. This is what we have been discussing now. You can map these translations and rotations or simple transformations. You can map using certain methods. So mapping can be done of mapping translations or pure translations can be done using this way. So imagine you have this this particular point, right? Initially, it's like this, right? Initially, this particular point is here with respect to the A frame, and suddenly you move this object to this point. So what you do is you replicate this entire coordinate frame to fit this here, right? In such a way that AP sort of equals BP in this according to this frame, right? I think you understand what I'm trying to mean here. So now here what we have is a separate frame, separate coordinate system. We call this frame B, right? Now, how do we compute the position vector between the position vector of this particular point with respect to the frame A, right? So since this is a pure translation, we can easily get the position vector between the origins, right? So here what we are trying to get is the position vector of the B frame's origin, which is this point, with respect to A. So you get this vector, and you know this vector, right? You know the position vector of this particular point with respect to B. It's generally going to be the same as, because there's no rotation here. The frame is like the mirrored version of this A frame. So if we know the position vector of this, it should be the same here, right? Because there's no rotation. The point has not changed, right? The point of interest has not changed. So you can find this vector as well, right? It will have the same x, y, and z coordinates here as well, right? Just that it's with respect to the B frame, right? Say it's 257. It's 257 is so basically the position vector will be px, py, pz, right? Say it's 257. It's going to be 257 here as well, right? Because this frame is a complete replication of what we have here, right? So we know this, we know this. So from your basic vector knowledge, so you know if this vector, if you know this vector is here, this direction, so this is this direction and this is in this direction, the resultant of this vector's addition will be given by this, right? So you simply have to add these two vectors. So position vectors are 3 by 1. So you know that the vector orders are the same, so you can add them. You will simply get the position vector with respect to A of this particular point of interest, right? So this you all know, I think, from your A knowledge. So now we'll talk about pure rotations. Rotations, it's not straightforward as above, right? So for rotations, to obtain the relationship between the rotations of Cartesian frames, we have derived these relationships called the rotation matrices, right? So once again, as I said, the derivations I'm not going to go through. You can go through the lectures where I have, I think, covered these in detail. But if you want further assistance in identifying these derivings, I suggest you all to use John Craig's reference book in Introduction to, the book's title is Introduction to Robotics. I think that's the book. I'm not exactly sure. Anyway, the book's title I'm not sure, but the author is John Craig, right? Introduction to Robotics and Controls, I guess. So yeah, this is simply the rotation matrices. So basically what this actually means is, say you want to find the, so this assume that there's only a pure rotation, right? In this, like in this case. So initially we have this frame, the frame A, and with respect to frame A, there's a particular point, right? This red dot. So what you do is you rotate the frame. The point is fixed. The point is fixed, but you rotate the frame. Now what happens? So it's vice versa, right? So imagine the frame is fixed, you rotate the point, and then you simply draw a coordinate frame identical to what was before to fit the point, right? Same thing, right? Same thing, but the approach or like it's like what has been rotated and what's static is the only thing that's different, right? So once this particular frame is rotated, in this case, once again rotated around all three axes, not a single axis. So you have to know the order of rotation. So in this case, if we assume that the rotations have been taken around X, Y, and Z, what you have to do is you have to see around by which angle it has been rotated around X-axis, and by which angle it has been rotated around Y-axis, and around by which angle it has been rotated around Z-axis. And then you simply compute these rotation matrices for these particular angles. So Rx will be, so say imagine it has been rotated around X-axis by 30 degrees, then theta here for Rx will be 30, right? So you have to calculate this, you are using a calculator using degrees, right, as the units, but in MATLAB Robotics Toolkit, you will have to use radians. So you have to use pi over 6, right? So then imagine it has been rotated on y-axis by 60 degrees, then you have to substitute 60 here and compute. And say 45 around z-axis, you have to substitute 40 here and compute. And then you get 3 rotation matrices which have been already computed, and you have to multiply them according to the order. So Rx into R pi into Rc, right? This order can change, right? Sometimes it can rotate around Rz, Ry, and Rx, or it can be Rx, Ry, and then again around Rx. Then you have to do the multiplication of the matrices in that order, right? You can't switch the order because you all know that violates the rules of matrices, right? You can't switch the order of multiplication. You have to go with the order that the rotations are taking place, right? So this is for fixed angle rotations. We will be talking about something called oil angles as we move on in the next sessions. So this is this with regard to the basic fixed angle rotations, right? So here, so you can see there's an example that I've done here. So here in this figure, frame B is like this. It's rotated around Z-axis by 30 degrees. So relative to frame A, Z-axis. So you can imagine that the Z-axis is pointing out of the book, out of the page, right? So we don't have to denote that. So anyway, it's overlapped, right? Z A and Z B are overlapped because it's been rotated around Z-axis. So by 30 degrees, right? So this angle should be 30 and this angle should be 30. Now, if you want to find, now this is pure rotation. You can see there's no translation. This is just a rotation around the z-axis that has been taken place, right? So what you do here, simply you can calculate the rotation matrix around z-axis, right? So you got this is the typical matrix for the rotation around z-axis. So this you have here. So you know the angle that is 30 degrees. You plug in the angle here, right? You plug in the angle here. So then you simply get cos. This is the shortened form for cos, right? Cos 30 minus sin 30, 0, sin 30, or this you can substitute all this and you can compute. You know, cos 30 is this value, sin 30, you know, is half. So you can substitute and you get this particular matrix. This is a rotation matrix, right? And now they're asking us to find this particular point, right? This particular point in space. So this is a point, this particular point, right? So the coordinates of this point has been given as, or the position vector of this point is given as this, right? Even if it is not given, you can still find it, right? You can still find it because so this with respect to B it has been given, right? The position vector with respect to B. So B is here, right? This is the B frame, B coordinate frame. So, and here I will, for your reference, I will draw the Z as well, so you are not confused. Is a Z axis, right? So with respect to this B frame, this only has Y, right? Only Y value is here. X value is 0, Z value is 0, only Y value is 2. Right? That's why this position vector is given as such, right? So you know the position vector here. Now you know the rotation relationship which is given by this. If you want to find the position vector of this particular point with respect to frame A, you simply have to multiply this by this, right? So it will be RAB. So B with the rotation of B with respect to A into this position vector of position vector of the particular point with respect to B. And once you multiply this, it's a simple computation, right? You will get this. So this is the answer. This is simply this point, the position of this point with respect to A, the A frame, right? So this is the A frame. So with respect to A, this is what. So you can simply, if you look at this in an intuitive manner, you can see you are getting with respect to this. So I'm talking about this frame, okay? So you can see that this particular point has a Y value, but yeah, so you can see this is the Y value, right? So Y value is positive, right? Y value is positive. But it is less than this value, right? Because it's the, if you look at this, it's this value is simply, if this is 30, this cos angle value of this, right? So that's what you get here. So it's going to be less than this. So yes, so it's correct, right? It's 1.732 is less than 2. And you can see the X value is in a minus range, right? Here it's crossing this line, crossing the y-axis of frame A. So it's in a minus range. It's correct, right? See, it's in the minus range. So z-axis anyway doesn't have any variation because it's rotated around Z. So here we have 0, right? So this is the position vector of this with respect to frame A, right? So this is clear. And now we have a combination of translations and rotations together, happening all together, right? So simply we can use this particular theory here as well. You can go through the derivations. I think you have done the derivations. Anyway, we don't care about the deriving, right? That's a problem for the mathematicians and the physicists. We just use it. If they say this is okay, you get the rotation matrix using this particular matrix, you just go and substitute, just plug in and you get it. That's it that we care about, right? But for your understanding, you can go through the proof and see how that's happening. Okay. So if there's a collection like this, you can simply, so there's frame A like this here, and it has been rotated and translated to this particular point. And there you want to find this B position vector, the position of this particular point with respect to A. So we know, so what we simply do is we'll first find the rotation, right? That's the general practice. We find the rotation. So we find the rotation with respect to A of B, right? We'll find the rotation with respect rotation of B with respect to A. That is being given by this rotation matrix, right? And then we want to multiply that by this position vector, and then we want to add this particular offset, right? Because we added the position vectors earlier. So once you multiply this is a 3 by 3 matrix. This is a 3 by 1 matrix. So 3 by 3, 3 by 1 multiplication, you get 3 by 1 matrix. This is 3 by 1 matrix. So 3 by 1, 3 by 1, you can do the addition because the order of the matrices are okay, and you will get the position vector. So sort of simplify this because we don't want this addition to take place, right? Because when there's an addition, it becomes complicated. First, we implement that in an algorithm, a continuous algorithm. So we prefer it to have as a multiplication. So we reorder the entire thing in this way, right? So the position vector A is given by the entire transformation. This means the rotation and the translation. This is given by this particular type of matrix. We call this a transformation matrix, or we call it the homogeneous transformation matrix. So once you multiply the homogeneous transformation matrix by the position vector of the point with respect to the current coordinate frame, you get what you require, right? So this transformation matrix is denoted in this particular form, where you have the rotation matrix and we have the position vector. And to get this homogeneous, the homogeneous matrix form, we have this 0, 0, 0, and 1, so that it gets that shape, right? So it gets the shape of the homogeneous transformation matrix. So since simply this is a 3 by 3 matrix, that is a 3 by 1 matrix, and this is made homogeneous by adding this and making it a 4 by 4 matrix, right? I hope that is clear. So now we'll go into the example that we discussed in class, right? And then we'll implement this in code. So simply it says frame B is initially coincident with frame A. Frame B is then rotated around YB by 30 degrees, then about XB by 60, and then about ZB by 30. So finally, the origin of B is translated. So here we have this particular vector, the transpose of it, right? So that is fine. Now we are supposed to find the transformation matrix of B with respect to A. And then using that, we have to find the position vector of this particular point given here with respect to B. We have to find it with respect to A, right? So this is simply the plan. So how would you approach something like this once you get a question like this? What you first do is you look at the rotations, right? So there's rotations, just 3 rotations, right? They first rotate around Y by 30, and then about X by 60, and then about Z by 30. So we list it down like here, 30, 60, 30. And also we know the position vector of this particular point, right? The origin of B is translated with respect to A by this. So we know this value is simply so position vector, position vector of B origin with respect to A, right? This is what we have. We actually want the transpose of this, so we put transpose here in our case because that's what we want, right? So, so this is what we want, right? So this is actually what we have been given. This is what we actually have been given. These are the data. So what we do first is, we know that we have to find the rotation matrices. We simply get the rotations around each axis one by one, right? So first it's r pi. So you get r pi here. You substitute the angle, this is 30 degrees. You substitute the values, and you compute the matrix for the rotation around r pi. And then you compute the matrix for the rotation around around x-axis, right? And then finally you compute the rotation around the z-axis, right, by 30 degrees. And once that is done, you simply have to multiply these three matrices, right? This into this into this. And if you use your calculator and you substitute these values, get the matrices done, then you will, and you substitute and you multiply all these three together, you will get this particular matrix, right? So this is the rotation of B with respect to A, right? So you can see the rotation matrix. Now, now we are supposed to find. The transformation matrix first, right? So the transformation matrix takes this particular order, right? So we know the rotations here. So we simply have to substitute these rotations. This entire 3 by 3 matrix, we put a command put here. And do we know this? The position vector of B origin with respect to A? Yes, we know that, right? So we know that too. That has been given. So it has been given as 10 minus 5 and 4. So that's what we can come and substitute here, right? This is the position vector of the B's origin with respect to A. So now what we do is, to get the homogeneous form, we have this row here, 0, 0, 0, 1. And then we got the transformation matrix. This is simply the transformation matrix, right? So this explains the transformation of frame B with respect to A, right? Now, if we want to find any type of point in 3D space, as long as we know the position vector of that particular point with respect to its new coordinate system, we can find it. Right? We can find it. So if we know the transformation matrix, and if we know the position vector of an object with respect to its new coordinate frame, which is this here, then we can compute the position vector of that with respect to the frame that we want, right? Or the neighboring frame, in this case of a robot. So, so what I have done here is that, since they want to find this particular point in space, they have given that as 6 minus 4. I think these values, just recheck when I'm mentioning. Yeah, 6 minus 4 and 1. This is the point. They want us to find this particular point's coordinates or the position vector with respect to frame A, right? So we simply got the transformation matrix, which explains simply the entire transformation, the rotation and the position both, right? The rotation, translation both. So what we do is, so we want to get this vector located with respect to A, frame A. So we simply multiply the transformation matrix by this, right? And by multiplying, what you get is this particular position vector. This is possible, right? This is is a 4 by 4 matrix. So to fit that, so we know the Persian vectors are always 3 by 1, right? They have basically three types of data. I mean, the Persian with respect to x, the Persian with respect to y, and Persian with respect to z. So it's a 3 by 1 matrix. This is all, right? But since we can't multiply a 4 by 4 matrix with a 3 by 1 matrix, this violates the matrix rules, right? We put a 1 here, right? We put a 1 here. So once you multiply all these, you get this position vector. So it's a 4 by 4 matrix into a 4 by 1 matrix. You get a 4 by 1 matrix, which is this. So this says this is the position vector of this particular point with respect to B frame, right? But we don't want this 1, right? Because you can't have a position vector with 4 types of digits, right? Just want 3. The position with respect to x, y, and z. We don't have a newly implemented, newly introduced, type of axis, right? We just have 3 types of axes. So we don't want to introduce new ones. So we just cut this off. And we get this. This is the Persian vector, right? This is the Persian vector that we want. So you put this here, you get it, right? So this is the entire sum. Hope it is clear for you. So if by any chance you have come across any issues while solving this, you can contact me, right? Now we'll see how we can implement this in a program, right? MATLAB. It's very simple, very simple. So you don't have to go through all this hassle, right? So the reason why MATLAB is there is so that we don't have to go through all this hassle. It's a simple, it's a calculator, right? That's what it is. I mean, if you talk about it I mean, it's not a calculator, but it's a very complicated tool. It's a very complicated software. But in our case, in this particular case, actually sort of makes things easier for us, right? So I will show how it is done. Now, first, okay, we'll go to the sum once again. So first, what we are supposed to do, we have to find the rotation matrices. So we are supposed to find the transformation matrix. So how do we find the transformation matrix? So we have to find the rotation matrices first. So rotation matrix, the general rotation matrix is the multiplication of these 3 matrices, right? So what we'll do is I will use the command window here because we can see the result 1 by 1, but you can simply implement this in an encode as well. So we will get the general rotation matrix. We will call a variable as r, right? R, and we will assign these rotations. So first we are rotating around y by 30 degrees, right? So we will put what pi. So 30 is pi over 6, right? Okay. Now we have to get the rotation around x by 60 degrees, right? So we will get dot x by 60 degrees, right? Sorry, 60 degrees means pi over 3. Now we have the rotation around z axis by 30 degrees once again. That means z by over 6. So I will just let it display. Let it come up, right? So some where I have got it wrong. Yeah, I have put this. I don't know what this is. I will just copy this part. Right. So if I run this, Let's clear this so that the errors are gone. Right. So now we have this matrix. So you can see, I just use the command window so that I can compare these, right? So you can see the rotation matrix that we got here, simply this, right? It's correct, right? That means, so we got 0.967, this is almost 0.967, 0.058 minus 0.25, 0.25, 0.433. So this is exactly what we got as the rotation matrix by our manual calculations as well, right? Okay, so now our first part, which is to find the transformation matrix, is done, right? Which is to obtain the rotation matrix. Now we are supposed to get the position vector of B origin with respect to A. This is already given, no? So this is already there. So we know this, right? So we will put the position vector, we'll say P, we'll say PA, sorry, P, is PB origin, right? So it's given by it's 10. So you know how to add this thing, right? So you can either go with like you can put the 10 minus 5 and 4 and get the transpose of this, or you can do anything that you prefer. So in my case, I just put this semicolon so that when I have to get in transposes, things are much more simple, right? So now we got our position vector as well. Now we have to implement the transformation matrix, right? We have to implement the transformation matrix. So we'll put it as T. So what's T? What's the transformation matrix? First, we have the rotation matrix, right? We have R. And then we have PB origin, right? Position vector of B origin with respect to A, which is this, right? Is this. So we go and paste it here. So we got the two lines. Now we have to get the bottom line, which is 0, 0, 0, 1. So now we'll see if we get our transformation matrix with this. So we can compare here with the one that we got. It's the same thing, right? So sorry, this one. So now our first part is complete. You can see how many small amount of code lines we require, right? So this is all. Now the transformation matrix is done. If you want to find, say they say, okay, you have to find this with respect to this now. So what you do is, in this case, I will use this. So I will use PB here. It's equal to 6 minus 4, 1, and we want another 1 added here because that's what we want to find, because we have to multiply by the 4 by 4 matrix. So it is so we can get the transpose of this. So say if I want to get the answer is I put this as PA, right? P is equal to the transformation matrix into PB, right? Which is this PB transpose, right? Because this is in this form. This is a 1 by 4 form. We have to convert that into 4 by 1 form. If you do that, we get the answer as this. Is exactly what we got here. 16.28 minus 6.1, 0.49, and 1. We don't want this 1. And our final answer is this. Okay? So you can see how simple it is, right? And how to go through all that hassle. So if we implement the M file, it's just this, right? This part. And then you get define the PB origin. And you define the transformation matrix here, like this. So once you define the transformation matrix, you simply have to, whatever the vector that you want to find with respect to this particular coordinate, you simply derive the vector like this, and you simply multiply, right? You simply multiply everything. So say, so I will add these all. I want to display this. So I will say PA is equal to P into PB. So it's just 6 code lines. I mean 5 code lines if I don't keep that. So based on, you would simply just have to replace the values. Say it's in 1, 3, -2, and 6 or 7, right? Simply run this, right? I'll go back. I will maximize this. So you simply run this program and you will get the answer. So, no, actually. So small error somewhere. Error. All right, I have to put the transpose here, right? Now should be fine. Right, so you can see that you can compute. Now this particular value you can, this is a random value that I put here, right? This particular value you can ignore. So this is the Persian vector, right? This is the Persian vector. This is supposed to be fun. That's why. You can't have 7. So you are supposed to have 1 here, right? So this is the Persian vector with respect to A, right? So you can simply, what are you wearing here? You are wearing here the position of the point in space that you are trying to find. You are intending to find the particular point in space, and you know the position with respect to the new coordinate frame. But you want to find it with respect to A, right? So it's like this. You have, imagine there's a robot like this. So this is A. Say there's an end effector here, right? This end effector with respect to B is moving here and there, right? Initially it's here, and now it's here. Now it's here. So and then it moves to some other point like this. So you can see that this is B, right? This particular point is B. All these points are B. So you can see that with respect to A, B is being translated, and at the same time, there are rotations happening around B as well. So as long as you know, if you are intending to find this particular point, the middle of the gripper here, if you know this particular vector, which is the position of this particular point with respect to B, and then you know this or the B frame origin with respect to A, then you can simply, if you know this, if you can initially compute the transformation between these two. After that, you simply have to get the coordinates of this particular point and put it here. And then you can simply get what the position vector is, which is this particular persistent vector we are trying to find. Right? Yeah. Right. So pretty simple, right? By using 5 code lines, you have completely solved a spatial description problem. So the advantage of this is you can simply use it for multiple. I mean, you are not going to use it for each and every point, right? You have to develop an algorithm where it manually calculates, automatically calculates for all the movements. So there are like such algorithms we are using, right? I just want to give you all the idea of why we are doing this and how this actually happened, right? The internal architecture of all this, right? So now, if you all understand what this is, then that's it, basically it, right? So you can simply find any point in 3D space if you know these particular parameters, which is the Persian vector with respect to the origin and the pressure matrix. And then you can compute the transformation matrix, and then you can find any space in 3D vector space as long as you know this, right? So I think that is clear. So you can vary these and play around with the program. You can try out new things, right? So yes, that's basically it for this particular session. So I will discuss about the remaining parts in the upcoming sessions.